Okay, good afternoon, everyone. I'm Xiaoguang from Colorado School of Mines, and today I'm very happy to be here presenting our paper, VoiceAttack Fingerprinting Voice Command on VPN-protected smart home speakers. So this is a joint work with my advisor, Dr. Dong Chen, and my lab mate, Keyang. So let's talk about the smart speaker first. Think about the most popular IoT devices in homes or buildings today. They must be smart speakers. They are almost everywhere, and the number is rising quickly. I believe many homes have more than one Amazon Alexa or Google Home. Actually, based on the recent data, as you can see from the graph here, the smart speaker market is projected to grow from $10.9 billion in 2023 to $35.6 billion by 2028, with a 25% annual growth rate. And this rapid growth is driven by the fact that smart speaker can be integrated with the smart home ecosystem, and they can easily combine with the other IoT devices, adding even more convenience for our daily life. However, this kind of smart speaker also raise some privacy issues, and this is not news. So next, we first look at how voice speakers work in our real life. As you can see in this diagram, this kind of devices generate a lot of bidirectional traffic, and which means the data flow both to and from the cloud server. Interestingly, even though the data is encrypted, this traffic may already carry some information about the voice command. And there has been many significant research working in this area. They have shown similar results. And so look at here, this shows 4 different graphics for the voice command. What's the weather like today? And as you can see, the traffic rates in the Vegas. So basically what happened here is user voice command has different patterns. And this pattern may have already embedded into the traffic rates data. And they are exposed to privacy threats. One of the well-known one is the fingerprinting attack. And here is a summary of the existing research related to fingerprinting attack. So the idea is attacker can identify the activity or commands being performed on the voice command, on the voice assistant using machine learning classifier. And if you look at this table, it highlights some of the most recent research. So while this work are effective and somehow very accurate, they still have some limitation that need to be addressed. And to summarize their limitations, first, a lot of these studies assume they are working with clean, isolated, or pure smart speaker traffic without any noise. But in real life, there are multiple IoT devices active online and creating noise. So most of the existing work wouldn't work well if they have multiple IoT devices running simultaneously. And also some of them depend on precise invocation detection. That is, they recognizing exactly when a command is issued, but with so much noise from other devices, this approach isn't really reliable. And in addition, most of these methods also require access to data like the IP address to tell which traffic belongs to what. And the other big missing here is no one actually talk about the similarity and sensitivity of this kind of voice attack, voice commands, and no one really look into the which commands are easier or harder to fingerprint. So guess what? This existing work are not really in real-world settings, and people may have multiple IoT devices running simultaneously, and users also started to use VPN to protect their IoT devices, and the current attacks will fail. So here the graph shows one example for the VPN encrypted traffic. And when a VPN is used, devices become hidden under the encrypted traffic. And as you can see in the graph on the right, the traffic is aggregated. That means we no longer have access to the data like the IP address. And the IP address are also hidden. And the existing work wouldn't work anymore. And VPN turns down everything. Again, we only have access to aggregated network traffic, making precise fingerprinting attack more difficult. So let me rephrase the research problem we are addressing. So we are answering the question of, can we design a new fingerprinting attack that on parts of the adversary could use to infer voice commands across different voice platforms, even in VPN protected environment? And to address all the concerns, we actually design the system in this way. So here is our pipeline. I will go through each step. So what I'm doing here is to address our first challenge. Like most of the traffic is hidden behind the VPN encrypted data, which make it tricky to analyze individual or per device data the traffic. And to address the biggest challenge, we actually designed a module to disaggregate the traffic from VPN. And with traffic disaggregation, even if multiple devices are active simultaneously, we can still pull apart the speaker traffic from other devices. And take a look at this figure. So in this setting, we have 6 devices. One of them is Amazon Alexa. And here we use a Terra LSTM model to detect and separate the Amazon Alexa traffic from other 5 devices. So you can see that the red line follows closely with the ground truth data shown in the blue line. And this demonstrates that our approach is sustainable and solid, performing effectively even in diverse home settings. So after we get the pure per device traffic, we further pre-process the data using lots of pre-processing techniques. For example, the trimming, resampling, filtering, and standardization. And when the data is ready, next step, we want to extract the key features that will help us build an effective fingerprinting model. Like we identify a set of principal features, and then we apply the principal component analysis. Now, if you look at the graph here, you will see that by the time we use 11 principal components, we already capture over 90% of the variance. And this means we can safely reduce the dimension from 66 to just 25. And by doing this, we optimize the model, prevent overfitting, and also reduce training time. And after extracting the most important features, the next step, we benchmark the most widely used machine learning and deep learning models in the literature. And we fine-tune all the classifier, and we find that the LSTM shows the bad accuracy. So the reason LSTM works so well is that it's designed to capture the sequential pattern, and which align perfectly with the structure of voice commands. And we ran this benchmark multiple times and found similar results from both Amazon and Google Home. And so confirming that LSTM is our top choice. So the last module in our system is command similarity and sensitivity analysis. So this module addresses the last challenge we have. Actually, it is a big missing in the current world, and we are answering the question of why are we able to effectively fingerprint some voice commands while struggling with others. And so to explore this, we use 3 similarity algorithms, which is WPIS and LIN. And this algorithm helps us understand how related different voice commands are at the semantic level. So here is our implementation. Like it has 2 main steps. First, we focus on data collection. Like we collected 200 unique voice commands organized in 20 categories, and which each category contains 10 specific commands. And this category aligns with the Amazon Alexa website, featuring examples like weather updates, location-based query, and also general knowledge questions. And as you look at this figure, to proceed the data collection, we actually we set up 2 Raspberry Pi. So one Raspberry Pi is playing audio to interact with the smart speaker, and another one run OpenWRT as a router with VPN to simulate secure environment. And while we use the TCP dump to capture the network traffic, and to avoid ethical concerns, we don't use human voice directly. Instead, we use the AI model to generate human voice. And secondly, for building the whole system, like we rely on some open source frameworks like TensorFlow, scikit-learn to implement the machine learning and deep learning models. And we also use Astronauto to generate network traffic for our defense system. And let me walk you through some evaluation results. Here, we use Amazon Alexa and Google Home. We use Amazon Alexa as an example to evaluate the performance of VoiceAttack under various home settings. In this figure, you can see that we're only using incoming traffic data to train and test the model at both the sentence and category level. Even as more devices, including some small IoT devices, are added, the fingerprinting performance remains robust, showing consistent trend across both levels. And this demonstrates the stability of our approach, and even in diverse home settings. And here is another example of our evaluation using Amazon Alexa under different home settings. And we test VoiceAttack performance using different directional traffic data. Unsurprisingly, combining incoming and outgoing traffic gives the best fingerprinting accuracy because it captures both structured responses from the cloud server and also the user trigger commands, providing a more complete view of the traffic data. And if only one direction is used, using only incoming traffic gives that actually also pretty nice results. It's better than only using outgoing traffic. So why using only incoming traffic can to train the model can get a better accuracy than only using outgoing traffic to train the model? So the reason is that incoming traffic is less affected by the user interaction and is generated and prepared directly by the cloud servers. And this makes incoming traffic more reliable and easier to fingerprint than outgoing traffic. And outgoing traffic is more unpredictable and noisy due to user behavior. So next, we look at the VoiceAttack performance on different granularities using both Amazon Alexa and Google Home. And we test the model accuracy at various time intervals, ranging from packet level to 1 second intervals. And x-axis show the data granularity, and y-axis show the MCC. And we can see that the model achieved nearly the same accuracy across different granularity, showing robust performance. And this time, we examine our VoiceAttack performance across different data portions. Like we adjust the amount of the traffic data used for training from 100% to 25%, and testing how different data portions impact the model performance. And as you can see, this bar graph, even we only use 25% of data to train the model still achieve reasonable results. And next, we talk about the voice command similarity and sensitivity analysis. So we first look at the graph here. We use 3 popular semantic similarity metrics like WP, IES, and LIN, and to measure how closely related to the related voice command are in meaning. And we perform sentence level inference and plotted each data point on this graphics, and showing it is prediction probabilities along with the corresponding semantic similarity matrix. So the result reveals that higher semantic similarity scores correlate with higher prediction probabilities, suggesting that commands with greater semantic similarity are more challenging for the model to differentiate, making accurate fingerprinting more difficult. And we also provide a specific example below, like we perform sentence level inference for the command, what's the weather going to be like this weekend, and achieve 71% of top 1 accuracy. Additionally, the top 5 accuracy is really high. It reached 97%, and with all 5 sentences all related to weather. So this shows that even if an attacker cannot infer the exact command at the sentence level, they can still determine the general category. And while the exact commands remains hidden, the ability to identify the category like the weather raise significant privacy concerns. And in conclusion, we decided a new fingerprinting attack could still accurately fingerprint voice commands at even in the VPN-protected environment. And we find that 134 voice commands are highly vulnerable to voice attack, and 3 commands are less sensitive. And due to the time limitation, I cannot present our defense approach. And we actually propose a proof of concept defense method. It's possible to mitigate the voice attack. And in our future work, we plan to expand our work by gathering more data, including other platforms like Siri. And also we want to provide some cost-effective defense method with very reasonable traffic overhead. And that's my whole presentation. Another thing I want to mention that is our data sets and source codes are open source. And I'm more than happy to answer any questions. Thank you.
Thank you so much. Questions from the audience?
Thanks for your presentation, Dr. Guo. So I have a brief question regarding what are the specific features that you would explore from the encrypted network to infer the voice command? Yeah.
You mean the how do we extract the features from the network traffic?
Yeah. And also, do you need to require the network inspection or other methodologies to get the data inside the packet?
We only need the network traffic rates data. So we don't need other information like the IP and some other communication protocol that's infos. Like we only need the traffic rates data, and we include a lot of principal features, including the basic statistic and energy and power tensor rates analysis, and we include like totally we have 66 features, and we apply PCA to reduce the dimension to 25. Okay. Thank you.
Any other questions? All right, thank you so much.
Thank you.